Okay, so good afternoon. Welcome to this Fellows webinar. Gillian is not present today, so she asked me and Sanya to chair this meeting. Welcome all. Today's lecturer is Professor Nadine Mattielli, a professor from ULB, Belgium. And her research interest, if I can say a few things about her. So her research is focused on the geochemistry of metal trace elements in the environment and the Earth's mantle, and also in the application of non-traditional stable isotopes, in addition to traditional radiogenic isotopes, as tracers of sources and processes of global biogeochemical cycles in Earth, environmental pollution, and paleoenvironmental reconstruction. Today's lecture is very timely, I should say. So the title is Rare Earth Elements and Radiogenic Isotopes from Mineral Dust in East Antarctica, Sensitive Tracers of the Atmospheric Circulation and Climate Variability Through Time. Here we already see the general title, Past and Modern Mineral Dust in East Antarctica. So Nadine, welcome. You can start.
Thank you. Thank you very much. So firstly, I would like to thank very much the Society for Environmental Geochemistry and Health for inviting me and to give this seminar with you today. So I would like to share 3 studies that we have carried out in close collaboration with several institutes and universities, as you can see on the slide. And all these studies are devoted to the geochemistry of mineral dust deposited in East Antarctica, and with the aim to really determine their geochemical composition and also the origin of this dust, and to reconstruct the present and the past atmospheric circulation in order to gain a better understanding of the climate change, and especially during the last glacial, interglacial transition. So probably the first question you would like to ask me is, but why are the dust so important? So the dust are really a key component of the Earth system because they are composed of reactive species affecting directly or indirectly the radiative balance, especially through the interaction between aerosols, radiation, cloud, and chemistry. And also, they are very efficient transporter of inorganic elements like iron or phosphorus, and also organic elements like bacteria. So they can really influence the primary productivity in the ocean, especially in what we call the HNLC ocean, so the ocean with high nutrient and low chlorophyll. And it is especially the case for the Austral Ocean, where the phytoplankton stock is quite small, and even the macronutrients are quite in high proportion. Some micronutrient like iron is really limiting. And so therefore the dust can really bring some iron to the ocean and can boost the primary productivity. And if the primary productivity is higher, then the ocean can really play a role of sink of the carbon dioxide and therefore can play a role in the climate. Also, the dust becomes a more major concern right now for the public health, because the anthropogenic aerosols, especially the black carbon, for instance, can increase the positive radiative forcing in the atmosphere, so they can increase the temperature in the atmosphere. And in addition, the aerosols can be really toxic for the health, so they can really enter in the lung, especially the fine particle, and therefore they can interact with the blood. But for this talk, we will focus our attention on the mineral dust, and especially the mineral dust included in the ice core. And why the ice cores? Because they are considered as really precious and faithful archives of the past paleoclimatic condition, the past environmental condition. We will especially investigate two ice cores from Antarctica, the EDML 1 and also the EDC, but a little bit less ice cores. Up to now, what do we know about the sources of the dust deposition in Antarctica? Currently, there is a quite strong agreement about the contribution of Patagonia as a real major dust contributor in Antarctica, especially during the last glacial maximum. But for the Holocene, it's really less clear, so there is no consensus. And many other studies proposed several secondary potential source areas, like, for instance, southern central western Argentina, north and southern Puna, southern Altiplano in southern South America. Also, southern Africa, especially the Etoshapan and Suapan, and recently the Namibian coast. But the southern Africa is really poorly known, so only 6 samples before this study were explored. In addition, other studies propose the contribution of Australia and New Zealand. And of course, in addition to the distal sources, you can have also the local sources, for instance, the nunataks, so the mountains from Antarctica. Those nunataks with the erosion can bring some dust in Antarctica, especially on the Pacific sector of Antarctica. So you can see that for the secondary potential source area, there are many open questions that remain still open without any answer. So up to now, to provide some answer, the publication use rare earths concentration or isotopes. So for the rare earths, they use often the ratios between the light rare earths versus the heavy rare earths, or the anomaly in specific rare earth, like for instance the European anomaly that was used in Gallero et al. And based on this anomaly, they can really discriminate the contribution of Southern South America for the Antarctic dust. There are also other approaches proposed in the literature. For instance, the approach from Marx et al. So they calculated the deviation between the source areas, the rare profile from the source areas, and the rare profile from the deposition area. So they use only the percentage in deviation. And the last approach was proposed by Wegner et al. So she proposed a triangular diagram built on the sum of the light rare earths versus the sum of all the rare earths, for instance. And so they play really with the sum of light rare earth, intermediate rare earth, and heavy rare earths to compare the potential source areas in the southern hemisphere and the Antarctic dust. But mainly in the literature, the publication proposed to use the strontium and neodymium and lead isotopes to trace the sources of the Antarctic dust. So here you have an example of the work from Rousset or Del Monte et al. And they really confirm the link between the Antarctic dust and the Patagonia as dust sources. You can see also in this diagram that the isotopic field for South Africa is extremely large, and it's based only on 6 samples, so it's poorly constrained. So in this context, we would like to investigate much more the role of the Southern Africa as a dust potential source area for Antarctica. We would like to provide a new, powerful, and sensitive tool based on the shape of the rare earth profile in order to provide a high-resolution quantitative model of the potential source area contribution in the I-score, namely the EDML I-score, over the last deglaciation transition period, so between 26.5 thousand years and 7.6 thousand years. Then we would like to validate this rare earth model with the isotopic results. And finally, I will present you the comparison with some results from EDML and some present-day snow dust results. So let's go, and I will start presenting the material and the methods. So you have already understood that we will use the EDML I-score and the dust preserved in this I-score. I will then present you also some results for the modern snow dust. And those modern dust samples have been collected during several sampling campaigns in East Antarctica from 2018 up to 2022. So during 5 sampling campaigns and along a transect of 200 kilometers from inland to the coast. So at 7 sampling sites, we have collected a large volume of snow to filter the dust. And in addition, we have installed a passive sampler, the Sigma 2 passive samplers, to collect the dust on filters and to be able to analyze the dust in the lab. So here you have a map of the transect. So we are here really in the drowning mode land, and the transect starts in the high plateau, across the area close to the Belgian polar station, Princess Elizabeth Antarctic, and it goes to the coast. And I would like also to share the very new news. So there is currently an expedition in Antarctica. Our students or PhD students is in Antarctica, and she will perform a snow pit at the coast to have a year-round record of the dust in the snow. And she has also installed a purpose-built automated seasonal passive sampler to collect the dust according to the different season during 1 year. So in addition to these Antarctic materials, we had the opportunity to measure, to analyze samples coming from Southern Africa. And why we think it's a very crucial zone to study, it's because up to 2070, the study report only dust composition from Etoshapan or Suapan in Botswana. And it's only recently that the study von Holt demonstrated that the coast of Namibia can produce a large amount of dust. And you can see here the comparison between a satellite image from 2017 and another image took in July 23. You can see that really the dust plumes are really huge. And so the production in dust are really important. It's important for the ocean, but also for the long transport of dust through the southern hemisphere towards the Antarctica. So we had the chance through a close collaboration with James King from University of Montreal to have access to 30 samples from the dustiest riverbeds along the coast from Namibia. So we have in the north, Omaruru in the center, then Kusep, and the Namibia Sand Sea in the south, a very sandy zone. So we have analyzed the bulk fraction for the rare earths and also the isotopes. And we have also separated the fine fraction using the Sésame simulation chamber in Paris-Saclay, through the collaboration with Paola Formenti. So we had the chance to collect the fine fraction of dust with a diameter of less than 11 microns. And we have also separated the very fine fraction from the Namibia Sand Sea samples with a simple method applying the stock law in the lab. So we obtain the rare earth profiles and also the dysprosium, neodymium, and lead isotopic data. I will come later to the results. So when we gather the rare earth data set, we have developed a totally new method. It is a statistical method based on the comparison between the rare earth pattern shape from the potential source area and from the EDML I-score, firstly. So the principle is as follows. So we collected the profile of 14 rare earths of the main southern hemisphere potential source area from the literature, and for our own data set from Southern Africa. So we had 207 rare earth patterns. On the other side, for Antarctica, we use the work of Wegner et al., with their agreement, of course. So they had 396 EDML rare earth pattern covering a very large time window from 26.5 thousand years up to 7.6. And then to determine the best superposition between one or several potential source area rare earth profiles and the DML profile, we developed an algorithm that solves linear equations based on least square method. And also to account for the uncertainties associated with the DML rare earth concentration analysis, 5,000 Monte Carlo simulations were carried out for each profile. And so applying this approach, we could really find the best fit between one or several PSA rare earth profile and a DML profile from each sample. So besides the rare earth, we have also analyzed the strontium, neodymium, and lead isotopes for the samples coming from Southern Africa and also for the modern snow samples. So now the results. So firstly, I will present the results of rare earth profiles from EDML compared with the main potential source area in the southern hemisphere. As you can see in this diagram, there is a significant variation in the total flux of dust from the last glacial maximum, so the LGM, to the early Holocene. So we see a drastic drop of the total dust flux, especially around 80,000 years. And we can see that we have a different profile starting at 14.5 thousand years. So it means that during the LGM, the composition of the dust shows some variability, but on average, it's quite a stable proportion of the different potential source area. And from the ashes 1 period, so the enriched stadial 1 period, the dust flux decrease and the contribution, the relative proportion of the different PSA, potential source areas, change drastically. We can see also that during the Holocene, it's not simple, it's quite complicated. You have a lot of fluctuation of the different source areas. Now, if we looked carefully at the different proportion of the potential source areas through time, you can see that it is sure that during the LGM, Patagonia is the main contributor to the Antarctic dust, so contributing to up to 68% of the dust. It is followed by Australia, then Southern Africa and New Zealand and Puna Altiplano from South America. Now, during the Holocene, from 40.5 thousand years, there is a drastic change, a drastic decrease of the Patagonia contribution. It decreased down to 44, and an increase of the Southern Africa contribution. Also, an increase for Puna Altiplano source area, and a small increase also of Australia. So during the Antarctic cold rivers, there is really a change of a contributor in terms of dust for Antarctica. Now, if we look at the isotopic composition, the isotopic results, we will start firstly with the characterization of the NAMIP samples. So here in this diagram, where you can see the strontium isotopic composition versus the neodymium isotopic composition, two groups are visible in correlation with the geological provenance. So firstly, you can see a large range of values for the NAMIP Sansi, the Omaruru, and the QSEP samples, dust. And that reflects the granitoid intrusion of Damara, which is a relatively young geological bedrock. So it's a neoproterozoic granitoid bedrock. In comparison, the UAP dust samples show a very narrow range, and it reflects more Paleoproterozoic paragneiss. So it's a very old paragneiss bedrock from the Kaoko belt, so a different geological unit. And in the lead-lead isotopic space, you can see that QSEP define the most extreme value with very strong enrichment in thorium versus the uranium concentration. Now, if we compare the Southern Africa isotopic signature with the South America signature, we see that the isotopes, especially the neodymium, but also the strontium or lead, the neodymium can really discriminate the isotopic field of the Southern Africa compared to Patagonia, for instance. Nevertheless, Northern Puna and Southern Altiplano overlap with the signature of a part of the Southern Africa samples. So now, if we compare now the Antarctic samples with the Southern America, Southern Africa, potential source areas, we see two very interesting trends. So firstly, here in green open symbol, the dust deposition during the glacial period show a quite homogeneous signature overlapping Patagonia. So the Patagonia is confirmed as a major contributor with additional input from other lower latitude areas in southern South America, like the Central West Argentina and the Southern Puna. This is what is observed for the glacial dust. Now for the interglacial period, we can observe a shift to lower epsilon neodymium values. So with contribution of more potential source areas. So certainly with the contribution of Altiplano North Puna and also the contribution of Southern Africa. And it is also the same trend that we can observe in the dust collected in the sediment core from South Atlantic. It's the work of Bayan et al. So you can see also the same mixing trend for the dust from Antarctica and the sediment in the South Atlantic sector near Antarctica. Now, if I can show you the present day dust result. You can see here in this diagram, again, it strontium isotope versus epsilon neodymium composition. You can see in red the data collected from the present day snow dust. And again, there is the same trend like for the interglacial dust, the same trend towards a mixing with Altiplano Puna and Southern Africa. So an important finding of our study is that there is a tree mixing hyperbola that we can draw with two common end members. So firstly, you have on one side the Patagonia as a one end member. It's a mafic-like end member because the plateau in Patagonia is mainly composed of basalt. And then you have a second end member, a crystal-like end member defined by Southern Altiplano. And you have a third end member, North Puna, and the average of the Southern Africa. Of course, Southern Africa define a large isotopic field, so we can define different average value to draw this mixing model. So how can we explain this trend from glacial period to interglacial period and the change of potential source areas? There are probably two hypotheses. So firstly, we can propose that there is a migration of the polar front. So during the interglacial time, we can propose, because the atmospheric model have already confirmed this hypothesis, we can propose a southward migration of the polar front, resulting in a decrease of the rainfall in the southern subtropical zone here. So those area becomes drier and becomes very arid zone, and then can produce dust that can be transported in the southern hemisphere. And it is impressive to see also that Altiplano and Puna and Wab or Namib Sansi, so the Namib coast, share the same latitude range. So this is a latitude corresponding to a tropical, subtropical location. And these regions are influenced by very strong atmospheric circulation dominated by subsidence air zones. So promoting extreme arid condition and producing very extreme desert lands. And reinforcing this aridity of this area is the presence of upwelling. So north flowing cold oceanic current. It's the Humboldt current along the west coast of South America, and the Benguela current along the western coast of South Africa. The second hypothesis we can propose is related to the transition that can be observed during the enriched stadial period. So several studies have demonstrated that during this period, between 40 and 12,000 years, the sea level rised of about 70 meters in Southern America. And therefore, the Patagonia shelf shrunk very largely. So it shrunk by about 70%. We have calculated that in our paper. And therefore, the dust produced by Patagonia is, of course, strongly reduced. Also, around 40,000 years ago, the drainage pathway in Patagonia changed drastically. So we saw a change from Atlantic to Pacific drainage pathway, and of course, its impact the sediment supply in Patagonia. And it's the same observation here represented for New Zealand. It's the same potential hypothesis that we can propose for this period. So finally, to conclude, I would like to share the main message to take home. So with our new rare earth model, we propose that during the LGM, so the last glacial maximum, the EDML demonstrates a mixture of dust sources coming mainly from Patagonia, plus Australia, and with minor contribution of Southern Africa and New Zealand and Puna Altiplano. While during the Holocene, we saw a drastic change with a decrease of Patagonia contribution and an increase of contribution from Southern Africa and also Puna Altiplano and a little bit of New Zealand and Australia. So certainly Southern Africa and also Puna should be considered as an important source of dust for the Southern Hemisphere and for the East Antarctic Plateau during interglacial period and the modern time. We have also compared the isotopic results with the rare earths results and our statistical mixing model based on the rare earth profile shape. And I think it's quite convincing that this model can be efficient and sensitive to provide higher resolution of dust sources contribution through time. And so as perspective, we would like to expand further the database from Southern Africa and Namibia and improve the characterization of the other source also in Southern Hemisphere. So thank you very much for your attention, and I am ready for question.
Thank you very much, Nadine, for this excellent demonstration of the power of the tools that we have at hand as geochemists today. So any questions from the audience? Everybody's speechless. Gillian, I see that you're raising your hand.
Thank you. I will. Nadine, lovely to see
Hello.
you. And I'm sorry I missed a fair old chunk of the talk. I might actually have missed something because of that. But my question to you is, I think I've got the last 10 minutes. What are the implications for the future, if any?
Okay, for the future. So it means certainly that the Southern Africa, especially the the entire country of Namibia will be even more dry than today. So I had the opportunity to spend 2 weeks in Namibia last month in December. And on the map, it was mentioned a lake. And we were looking for that lake, and it has totally disappeared. So yes, I think the aridity of those areas will be stronger and stronger, so it will increase the dust event and the dust plume. It can be a benefit for the climate, because usually the mineral dust can decrease the forcing for the radiation, but it can create other problems. And of course, for Namibia, it's not a very good news.
No, thank you for that. Thank you.
I see David Ernst has a question.
Yes.
David?
Yeah, thank you very much for that interesting talk. So I have a practical question. How did you actually analyze the rare earth elements, and how much material did you need for the analysis from the dust?
Yeah, good question. So the beauty of the rare earths is that you need a much less amount of samples compared to the isotopic analysis. So usually we can work with a very low amount of dust. So for instance, the dust filter for the rare earth analysis, we can cut the filter in 2 pieces and keep only 1 piece for the rare earth. So we can go to very low amount of samples to get still very precise rare earth analysis. It depends on the instrument you will use. So if you use an atom, ICP-MS, or an element 2, if those instruments work well, you can reach really low, very high sensitivity, and so high precision with low sample amount.
Okay, thanks.
Thanks. I can see now a question in the chat. It's from Dominique Weiss. So the question, after congratulating you, is have you seen some zircon grains in your samples? And would you be able to do LA in situ for some dating? Laser ablation, is this LA?
Yeah, very interesting question. So we suspect some zircons in the Southern Africa samples. For instance, in QSEP sample. So it's one of the reasons I spent several days in Namibia in December, is to get more samples to be able to make mineralogical analysis and maybe to isolate zircons. Up to now, we were focused only on to purify the samples and to isolate the fine fraction of those sediments to be able to have the most representative samples of the dust that can be transported on long distance. But indeed, I would like to know more about the mineralogy of the Southern Africa samples. In Antarctica, we have observed the dust with SEM EDS, and we have never seen zircons, only quartz, feldspar, micas, ferromagnesium silicate, clays. but up to now, no zircons, unfortunately.
Maybe does it have to do with a specific gravity?
Yes, yeah, I suspect,
Okay.
yeah, I suspect that indeed, as a zircon is quite dense and can be with a coarse, it can be preserved in the coarser grain fraction. So probably the zircon can stay in the source areas and not transported over a very long distance. So I suspect that in the sediment from the source areas, we can still find some zircon, but I will be very surprised to see some zircons in Antarctica because of the distance, except the zircon from local rocks, of course.
Mhm.
But the signature will be different.
I see another question by Saka Operloye. Why is the percentage value of the dust keep decreasing with age and that of SA increasing? South Africa, I presume, increasing.
So so you mean the total flux firstly, and then the contribution of Patagonia? I think I missed the beginning of the question. Sorry.
It's about the percentage value of the dust and the age. So this is keep decreasing with age, and that of South Africa increasing.
Okay. So the so the dust flux decreased certainly from the LGM through the Holocene, simply because of the deglaciation, because during deglaciation, you will decrease the amount of dust produced by the glaciers. That for sure. That's one point. So that's one thing. Now, to explain the decrease of Patagonia contribution and increase of the Southern Africa, maybe I can show again. No, I cannot. No, I cannot share my screen again. So as I explained in the 3 last slides, either we can propose that it is related to the shift, to the move of the polar front. So if the polar front move northwards, then the Southern Africa will encounter a weather condition, so an increase in rain precipitation. But in contrast, during the interglacial, the polar front can move to the south. So then the Southern Africa becomes drier and drier. And so Southern Africa can produce more and more dust. Now, in terms of air mass circulation, of course, it's a question of trade winds. So the dust coming from Southern Africa must be transported by the westerlies after the transport by the berg winds, because there is a strong berg wind coming from inland to the coast in Namibia, so they can transport dust to the so from the east to the west, and then the trade winds can transport the dust to Antarctica through the circumpolar winds. It's quite complicated, the atmospheric circulation, but you can follow the atmospheric circulation and the circulation of dust through the application Earth-0. You can really see the transport of the dust in the atmosphere at a different altitude. And of course, for efficient transport of the dust from Southern Africa, the best will be that the source areas will be located at quite high altitude, which is the case for Etoshapan and also for a large part of the country, actually, because Namibia is quite at high altitude.
Okay, maybe we are running out of time, but I see Sanya is raising her hand. And then
Yes, thank you, Nadine. Quite a fascinating talk on dust.
Thank you.
I was just wondering about mainly the molecular composition of those dust particles, whether you've investigated that and potentially have done any single particle analysis.
Yes, we performed some single particle analysis with CNRS for the Antarctic samples. Yes. So we performed some analysis from the dust coming from inland and also dust collected at the coast. And the mineralogies were different. Yes.
Okay, and are you using the Candler principle of chemical association to clusterize those, or what kind of
Yes,
methodology?
clustering.
Yeah,
Clustering.
just clustering.
Yes, yes,
Okay.
yes. And yes, and with the CNRS, we control the shape and the size of the particles also.
And there is another question from Matteo Serra. If you have looked at bacteria in the dust particles from the ice cores.
Yeah, yeah, I am absolutely not a specialist in bacteria or organic chemistry. Yes, of course, it can be very interesting to see if fungi or bacteria can be transported with the dust. And yeah, but really, I cannot answer to this question. I am really sorry. Yeah. I have a colleague from Ghent who work on the VOX, so the organic component, but not on the bacteria. But it can be very interesting indeed. Yeah.
Just
sorry.
to add a bit more complexity.
Yes. Yes.
If I can ask about the financial resources you need for this research.
Yes, yes. So yeah, we are lucky to have Belgian scientific political institution, and this institution can offer funding for the polar expeditions and also for the research. The competition is quite hard, but it's possible if the research program includes researchers from the north and from the south of the country, and also the national institutes. Then after very difficult selection, you can receive some funding to go in the field and to make research.
Can you give us a sense of the cost of this research, maybe?
You mean
The
the
actual cost.
okay. The cost, if you want to go there in Antarctica, for one people, it's about 60,000 euros. So including the flight and the stay in the station. So it's quite expensive.
Okay, I think we should close this session. We really, really thank you. This is such an exciting research.
Thank you very much. It
The
was
way
a
you
pleasure.
have put all this data together to come up with a model. Yes, I think, yes, you deserve a big applause from all of us. Thank you very much.
Thank you very much. I am really happy to see you. And yeah. So do not hesitate to send me any question. I can send you the papers also if you wish.
Excellent. Gillian, do you want to close this and say goodbye since you're here?
Thank you. I'd actually really like to say thank you to you for stepping in to chair it, and to Sanya for being on standby if anything went wrong. Thank you both very much. A huge thank you to Nadine for providing us. I'm so sorry I've missed the first part. I'm now looking forward to going and picking up the recording and seeing the first half. That was really great. And I doubt very much whether you said anything at all about the fact that you are now our new chair, did you, Ariadne?
Well, it's still we have a few weeks to go.
Not very long, but it's really nice to see you in that capacity as well. So a great day all round. Thank you very much, everybody. Thank you for the presentation. Thank you for attending. Thank you for the questions, and may we keep moving forwards.
See you soon. Bye bye. Bye bye. Thank you.
Bye. See you all next time.